part 2 of Cartesian vectors, which I believe leads us into part 3 of Cartesian vectors. What we're going to do now is we're going to make some equations of lines and planes using vectors. And this note is on equations of lines in 2-space. Where's my pen? Why is this not working? There it is. And I'm going to follow this up with another note on equations of lines in 3-space. So the first thing you need to know is the definition of a direction vector. So a direction vector of a line is a non-zero, so it has to have some sort of magnitude. A non-zero vector indicated usually by M with a vector line across the top because it's a direction vector, and it's parallel to the line that we're talking about. So this is a direction vector because it's parallel to the line, which I've indicated here in red. So the direction vector could be anywhere, it's just telling you the direction of the line. So if your line were in a different spot, you still have the same direction vector, you've just got a different spot for it to be going through. So any non-zero scalar multiple of the vector shown can also serve as the direction vector. So that means that this direction vector could be, 2, -2. It could be 3, -3. It could be 1, -1. What I like to do is I like to have it in its most reduced form. So the smallest non-zero scalar multiple, meaning a multiple of 1. So that's my tendency and most textbook tendencies. All right, so let's look at some stuff. First example says, determine a direction vector for the line that passes through the points A, 7, 3, B, -11, 8. So we're looking for the M. And that M could be AB. And this leads us back to the last unit of Cartesian vectors, where you have to take the second point and subtract the first point. So -11 subtract -17 is -18. 8 subtract 3 is 5. So the direction vector for this is -18, 5. There is also the possibility that you might have found BA, vector BA, in which case it's +18, -5. So because we now have a direction vector, we can describe a line using vectors rather than a line using points that we've been doing from, I'm going to say, grade 9 to now. All right, so next slide. A vector equation can be written in 2 ways. So you can either write xy in square brackets equals a position vector x1, y1 plus some value that is a scalar multiplied by the vector m. So this right here is vector m. So that's your setup. Alternatively, you don't have to write x, y. You could write r with the vector hat on top of it. So what we're going to do is we're going to give you an example of this. Now, I do want to mention to you beforehand that this answer is not unique. There are many different vector equations for the same vector. So you could have an answer that is not in the back of the book and still be right. All right, so determine the vector equation of the line that passes through the points A, 13, 8, and B, -5, 12. Now, I'm just going to move part B out of the way, assuming I can, and yes, I can. Before I go on, I just want to remind you, or I guess tell you, because you haven't done this before, that sometimes books people in this particular section get super sloppy about the type of brackets they're using. So sometimes they turn into round brackets, sometimes they turn into square brackets. There's a whole lot of inconsistencies when it comes to that, and I'm going to try to be consistent and use square brackets the whole time. So the first thing I'm going to do is find my vector m, and I'm going to choose to find my vector m AB. So I'm going to do my scribble work here. So B comes first, because that's where we end up, then A, and then I'm going to subtract. So this is negative 18, and this is 6. Now you could use negative 18 comma 6, but because this is a vector, we could use a scalar multiple, meaning that I could reduce this because it's still going to tell me the same direction. So I could divide by 6, and use lower numbers. It's up to you. And that's part of the reason, only part of the reason, that you have a non-unique answer, because sometimes people will do that and sometimes people won't. Another reason that a vector equation is not unique is because we need to pick a point for this position. And it doesn't matter whether you pick point 13.8 or if you pick point negative 512. This can't be reduced, but that's why you can't say that you have a unique answer, because half of you might pick A and half of you might pick B. So I'm going to use A as my point and make a vector equation. So I'm going to do it in blue so it stands out from what I've done. So x comma y equals, I'm picking 13 comma 8, and I realize that 13 comma 8 is a point, and now I'm putting square brackets around it. It is because this is actually O to P, meaning from the point back to 0, 0. So if I do the same sort of subtraction as I pulled off here, this would turn into a vector with the exact same components as the coordinates given originally. So then I continue, so plus t, and I'm going to make a fancy t with a little curl on it so it doesn't look like a plus sign. And then I'm going to write down, I'm choosing to write down this. Now remember, there is a second answer, and this is not the non-unique part of it. The second answer is using the r instead of the x comma y. Oops, there's me being careless. There we go. I realized that there are some important notes on the following pages. So the next thing we want to do is teach you how to make points on a line, or on this specific line, using this kind of equation. Way back in the olden days of not grade 12, you would have made a table of values. What you do now is you pick a value for t. So my recommendation is to not pick t equals 0, because that will knock all of this out, and create for you 13 comma 8, and that's not another point on the line. So we're going to pick something else. I'm going to pick t equals 1. So if t is equal to 1, this goes back to the other Cartesian vector unit, where if you have a scalar multiple, you multiply the vector by that number. So 1 times that bracket is itself. And then you add or subtract x values, and you add or subtract y values, depending on what's being asked. And there's another point. We need to pick a second t value to find a second point on the line. What is important is that you try to stay away from a t value that creates the point you didn't use. So I need a t value that doesn't get me x is equal to negative 5. So I think I'm going to use t is equal to -1 just to practice using negative numbers, which is actually quite a bit more complicated than using positive numbers. You can absolutely make more mistakes. So I don't know if you remember me doing this in the first Cartesian vectors unit, but my suggestion was that you multiply both numbers, both components by -1 and add instead. So that's 3, -1. So 13 plus 3 is 16. 8 plus -1 is 7. So we've found 2 other points, and when I list the points, even though I've done all the work correctly here, when I list the points, I should probably use round brackets. 2 other points are. So I was consistent in my work, but then I need a therefore statement saying I know the difference between points and vectors. Now, that is 2 other points of like a billion other points. So I managed to find 2 that are not here. Okay, so now let's check the important notes on the following pages. So you need a direction vector and a point on the line. Like I said, we could have used the other point, and this would have created a different equation, which makes vector equations non-unique, meaning there's lots of them. When you go to find other points, you choose any value for t that you feel like, and you substitute it into the equation. These 2 points should be other points on the line, so you do have to double check that you don't pick a t that gets you the second point that you didn't pick. Each choice of t produces a different specific point on the line, and t has a name. It's called the parameter. So it adjusts for different points. So t is called a parameter. So what that means is this, that x is equal to x1 plus t times a, and y is equal to y1 plus t times b, either written like this. I prefer it written like this. This set of information is called parametric equations, because there is more than one of them. There's one for the x, there's one for the y. Next page, parametric equations of a line passing through point xy becomes a position vector OP, same x, same y, having a direction vector, so you still need a direction vector AB, and there's your parametric equations. Now, here is the problem I have. I kind of need to make the vector equation and then make the parametric equation. That's the way my brain works, so that's the way I will continue to do this. So, question 3. For the line passing through the points C, -4, 13, and D, 9, 2, determine parametric equations. So I'm going to pretend this isn't here for a minute, and I'm going to concentrate on parametric equations. So the first thing I have to do is I have to find myself a direction vector, because if I go back to here, it says we need a direction vector and a point on the line. Presently, we have 2 points on the line but no direction vector. So I am going to find vector CD and get myself an answer for that, which means I need my scribble space. I'll do it up here just because I have some. So D, then C, and subtract. So that's 13, comma, -11. No reducing necessary here because you can't. So that means for me, I have a direction vector sorry, I have a direction vector of 13, negative 11, but I have a vector equation of xy equals, pick a point, I'm going to pick this one because it's all positive, 9 comma 2 plus t multiplied by vector 13, negative 11 that I created as my direction vector. So that is a vector equation, non-plural. And I say non-plural because there's only one of them. However, when you get to do parametric equations, it is actually plural. And I said that in the last slide, but I want to show you how that happens. So we can take this one equation, if your brain works the same as mine, and I see it as tearing it apart. So x is equal to the x from the first bracket plus the x from the second bracket with the t. And y is equal to the y plus the y with the t. So I'm actually going to put minus 11t. And technically for this, both of them, technically you should tack on that t is any real number to say that it's a parameter. All right, let's look at the scalar equation. This is, I don't know, I think this is kind of awesome because it links a whole bunch of math together. Some of you are not going to like this, but oh well. So I want to write down this again. Remember, you could have had dc is equal to components negative 13, positive 11, but I decided to do c to d. And what we did to do that is we did this math, as in we subtracted the x's and we subtracted the y's. So this value right here is the change in y, so it's actually y2 minus y1, and this is the change in x's, so it's x2 minus x1. And because I maintained order, what that means is that the direction vector in 2 space is the same thing as the slope, only you have to put the y's on top and the x's on the bottom and make sure it's reduced, which it is. So whoever picked m as the symbol for the direction vector and put a little vector hat on top of it was brilliant, because they came up with the same letter as slope. And a scalar equation, for lack of a better way of saying it, is a normal equation. Normal, regular, grade 9 to 11 equation. So what we do to find a normal, regular equation is we do y equals mx plus b. And all I have to do is pick a point. So I'm still going to go with 9 comma 2 as my point instead of negative 4 comma 13. So that means that my x is 9 and my y is 2, just so I have everything visible. And I do what we did at the end of advanced functions. I do what we did in grade 9 and 10 math to find the equation of a line. It's all the same stuff. So here's y, here's m, here's x plus b. So that's 2 equals negative 99 over 13 plus b. So that's 2 plus 99 over 13 equals b. 2 over 1 is the same thing as 26 over 13 plus 99 over 13 equals b. So that's 125 over 13 is equal to b, and now I can make my equation. So this is an equation. So it's y equals negative 11 over 13 x plus 125 over 13. And that is y equals mx plus b, which is known as general form. And we went through this at the end of advanced functions when we were doing limits. That's general form. Remember that there's another form that you can go through to find, and that is standard form. So I'm going to go through that right now. First thing I would do is I would notice or create a common denominator. So in this case, I've got a denominator overall of 13, so I'd write it like that. Then I would do a cross multiply. And the rule is that you're supposed to start with the x's and they're supposed to be positive. So I'm going to take everything that away. So positive 11x, positive 13y, negative 125 equals 0. And that isn't general form, it's standard form. And standard form symbolically is ax plus by plus c is equal to 0. And if you're thinking, oh, ABC, quadratic formula, these ones are capitals, quadratic formula, lowercase. We make a big deal about that. So the only thing you do have to double check right now is that you can't reduce this. So can you divide 11 and 13 and 125 by the same number? If you can, you're supposed to do it. I can't, so I leave it and I'm done. And that's my standard form versus my general form. Notice that this particular question doesn't tell you which form it is. It just says find a scalar equation. So it's kind of your choice. All right, next slide. Important and helpful hints. Important notes and helpful hints. So parallel lines have direction vectors that are the same or are scalar multiples. So it's just a case back here that if you've got a line and it's sitting here, that you find yourself a direction vector and then you find yourself a point on the line, and that makes it semi-unique. Remember, there could be another point on the line, but it's a unique line even though there's not a unique answer. This m, let's see if I can do this. I can. Could be any length at all. We try to go for the shortest length, meaning the reduced version. For me, I did that here when I decided to take my vector negative 18, 6 and turn it into vector negative 3, 1. That is doable with vectors, but is not doable with points. You can do that with components. You cannot do that with coordinates. Perpendicular lines, just for the future, have direction vectors that have the pattern switch the x's and y's and switch the signs. Now, maybe you know why that happens. I know why that happens. And it's because in this example right here, when I magically turned my direction vector into my slope, it was y's on top, x's on the bottom. If I wanted a perpendicular line, I need the negative reciprocal, and the negative reciprocal means upside down and opposite sign. So upside down of this, a positive instead of a negative in this case, and that would make the direction vector x, y. So it's switch the x's and y's, switch a sign. So switch one sign. Quick way to ensure that the dot product is 0. So if you took, or if I took, I guess, if I took this and I dotted it, so multiplied the x's, multiplied the y's, add them together, I should end up with 0 because the dot product being 0 is a characteristic of perpendicular lines or perpendicular vectors. In this set of homework, you might run into this stuff. I realize this is 3 space. Give me a sec to adjust. So parallel to the x-axis means a direction vector of 1, 0, 0. Parallel to the y-axis in 3 space is 0, 1, 0, and a vector parallel to the z-axis in 3 space is 0, 0, 1. Now, I just finished a note on 2 space. So there. This is the information you need about direction vectors parallel to those axes. Let me erase that. Okay, so that is this note, and the next thing will be equations of lines in 3 space. So we will end up using all of this rather than part of this. So maybe note it down now so that when I come across an example in the next note, you aren't confused about why I'm using one of these. Not saying it's going to happen, but it might.